Good morning and welcome to LVS Perspectives number 50, Maths to Infinity and Back. And I'm really proud to introduce Colin Stuart to you this morning, who's been spending some time with our pupils this morning.
Yes, I had the juniors first, and I've just had year 7 to 9.
Brilliant. Halfway through your day.
Yeah, it's good so far. Having fun.
Brilliant. Thank you. Well, I'm just going to pass over and I can't wait to listen to what you've got to say.
Okay, well, so this is an insight into the talk I've given to the older group today, right? Talking about infinity. So it starts like this. You find yourself stuck in the gravitational clutches of a black hole. You can kind of see what's going on, but your view is slightly murky. There's something going on in the center, but you can't quite see what it is. There's hot gas flying everywhere. But you're being pulled closer and closer by gravity until the view clears and you see the black hole itself. You don't know it yet, but you've just passed the point of no return. The point where it's impossible to escape from this black hole. At this point, the gravity is so strong on your feet compared to on your head that you get ripped apart, stretched out lengthways into long, thin strips of human spaghetti. And this is what would happen to you if you got too close to one of these objects, a black hole. Perhaps the most extreme and violent thing in the universe. And to explain what a black hole is in more detail, we need to have a look at different types of objects in space. So let's start with something quite familiar to us, which is the sun. At primary school, we're normally told that the reason why the Earth goes around the sun is because there's some kind of pull going on, that the sun is pulling on the Earth. But actually, we've got a better idea than that. It is actually that the sun is distorting the space around it. So the analogy would be here to imagine holding your bed sheet tightly at the corners, and then you place a bowling ball in the center to represent something heavy like the sun. You could then take a tennis ball and roll that tennis ball around the rim of that dip. In other words, you could make the tennis ball orbit the bowling ball. There's no pulling going on. It's just that the bowling ball is changing the shape of the sheet and the tennis ball is following it. That's how we really think about gravity. So this dip in the sheet, physicists call a gravity well. And you can see the sun's is fairly modest. But when stars start to die, their gravity wells become considerably deeper. So a neutron star is what you get when a medium-sized star dies. A black hole is what you get when the biggest stars die. So you can see there for the black hole, the well is so deep that once you're in, you're in. It is a trapdoor, a one-way ticket. There is no clambering out again. The well is so deep. But where do you go? Let's say that you make the fateful journey that we saw in the video at the beginning. You get sucked into the black hole, torn into spaghetti. Where do your bits of human pasta go? Where do you end up? In other words, what's at the bottom of a black hole? Well, far from the black hole, space isn't very curved. The sheet is quite flat. But the deeper and deeper you go in, the more and more curved it becomes. Our best theories of black holes come from Einstein and his general theory of relativity. And what the equations say is at the bottom of the black hole, space becomes more and more curved, and at the very bottom is something called a singularity, a point of infinite curvature, of endless curvature. And so it's here that we come across this notion of infinity for the first time. I think it's something we've all heard of, maybe even in the playground at primary school. There's that kind of competition between children. What's the biggest number you can think of? I can think of a trillion, I can think of a quadrillion. Someone always pipes up and says infinity. Technically they're wrong, because infinity isn't a number. It's just the idea of endlessness. So the counting numbers, if you kept counting, you'd never finish the list. It just goes on and on without end. We say that it's infinitely big. And so at the bottom of a black hole, space seems to be infinitely curved. The other thing we'd like to know is how, I said the sun was quite dense, the neutron star is a bit denser, the black hole is even denser, that's why it makes such a deep well. What is the density of the singularity? Well, we work out density by dividing mass by volume. We're talking about how much stuff there is in a particular amount of space. Except in this case, this singularity, this speck, has 0 size. So we're dividing by 0 in this case. The mass of the black hole divided by 0. If you've ever tried to divide by 0 on a calculator, you can try it on your phone now. It will give you the answer error. It can't do it. It will return an undefined answer. And the reason for that is that, let's say we divide 1 by smaller numbers. So we start dividing by 1 by a half. Another way of saying that is how many halves are there in 1? So the answer is 2. There are 2 halves in 1. If we divide by a quarter, well, there are 4 quarters in 1. If we divide by a hundredth, there are 100 hundredths in 1, and 500 500ths. So you can see in the left-hand column, we're dividing by a smaller and smaller number. We're getting closer and closer to 0. And as we do that, the number on the right-hand side, the answer goes up and gets bigger and bigger and bigger. So you might think, when you actually divide by 0, the answer you get is infinity. But not that straightforward. Because let's stick in a minus sign instead and divide 1 by minus a half. Well, then we get minus 2, and minus 4, and minus 100, and minus 500. So as we get closer and closer to 0 this time, we're coming in from the negative direction, but we're still getting closer to 0. The number on the right-hand side is now going towards minus infinity. So, well, which is it? If you divide something by 0, do you get the answer infinity? Do you get the answer minus infinity? No one knows. So that's why your calculator will return error or undefined when you try and divide anything by 0. So the density of the black hole is undefined, or error, or simply don't know. And if you ever get that answer, then it's telling you you're wrong. It can't be right. Whatever theory is giving you that answer can't be the right one, because how can it be undefined or simply don't know? So what is at the bottom of a black hole? I would say is probably not a singularity. Maybe we'll come up with a better theory one day that tells us what's really down there. But for now, singularity is the best we've got, this infinitely small speck, but it comes with a lot of problems. So infinity is a really useful thing in astronomy. When it crops up, as it does a lot, it's normally telling you you've got it wrong, that there's a piece of the puzzle that you're missing. So it's a very useful kind of neon sign that points towards that. Now, black holes are not the only place in the universe where infinity appears. This is Edwin Hubble. You may have heard of the Hubble Space Telescope, named after him. Back in the 1920s, he discovered that the universe is expanding. It's getting bigger over time. And he discovered that because he noticed that more distant galaxies appeared to be moving away from us faster. And from that, he said, aha, the universe is expanding. Now, it's not always obvious why more distant galaxies moving away faster are making the leap to an expanding universe. That logic is not always presented, so let's nail it. Let's nail it with something a bit more everyday. Bread, specifically raisin bread. So you're baking, you make some dough, stick in some raisins, and then you put it into the oven for an hour to bake. And in that hour, the dough will double in size to give you your raisin bread. I want you to imagine that you put yourself on one of those raisins, and then imagine what you'd see as the dough expanded in the oven. Because if there was a raisin that was 1 centimeter away from you to start with, then it would be 2 centimeters away after an hour, because the dough has doubled in size. If it was already 2 centimeters away at the beginning, it would then be 4 afterwards, 3 to 6 and 4 to 8. We're just doubling the distance over an hour. But look at the speed that the raisins seem to have moved away from you in that time. The nearest one, its apparent speed seems to be 1 centimeter an hour, because it's gone from 1 to 2. But the most distant one seems to have sped away at 5 centimeters an hour. In other words, more distant raisins move away faster in the same amount of time, or at least seem to. Why? Well, the dough is expanding and spreading out the raisins. You could do exactly the same here for galaxies, and that's what Hubble did. The distance, the closer they are, The slower they seem to be moving, the more distant, the faster they seem to be moving. Just like the dough, the universe is expanding. This is how Hubble came to that conclusion. This isn't always kind of laid out properly. Now, the fact that the universe is expanding leads to something quite interesting. It's getting bigger every day. So yesterday, it was smaller than it is today. And then a week ago, it was smaller than that. 100 years ago, it was even smaller. 1,000,000 years ago, smaller still. You can keep rewinding the clock until you get back to a point where the expansion started, where everything in the modern universe, as big as it is, was concentrated down into an incredibly small space. A singularity, again. We get the same singularity if you rewind the expansion, with all of the problems I've laid out, with the density being don't know and all those sort of things. This is better known as the Big Bang. The idea that our universe began as a very small point, burst outwards, and has been expanding ever since. But it's not a perfect theory, the Big Bang. I'm not saying it's the wrong theory, but there are issues with it. These are questions I get asked all the time about the Big Bang. If you can accept that there was this tiny point that exploded outwards, well, how can something come from nothing? The singularity had zero size. So how did everything in the universe come from something that was literally nothing? What happened before or caused the Big Bang? Before is a time word. So the Big Bang says, the Big Bang was the beginning of space and time. So how can you ask what happened before time existed? Doesn't make any sense. You can't ask what happened at a time before time existed. So you get in these logical knots with the Big Bang, or even where did it happen? Remarkably, and why this is a maths talk, and why I've been talking to the maths classes today, is that the answer to these questions, or at least one answer, comes from something as simple as a triangle. And the question I asked them just now was, how many degrees are there in a triangle? And someone correctly piped up and said 180 degrees. It's only half right, though, that answer. A better answer would be, it depends. Depends how you draw your triangle. Because yes, a triangle like the one you can see here, the angles do add up to 180 degrees. And we can prove that very easily without doing any numbers whatsoever. Take a triangle, label the angles A, B, and C, copy the triangle, make a second one, the same. Make a third one, turn it upside down between the others, and now you have those angles, A, B, and C, all together, and they make up half a circle. So we talk about doing a 360 in life, going around once, 360 degrees in a circle, half a circle, 180. So you've not even done any numbers or equations here, you've just made copies of triangles. It's very easy to show that it has 180 degrees. Not all triangles do. Here's a triangle. Let's say you're on the North Pole and you make an expedition down to the equator. And when you get to the equator, you take a 90-degree turn along it. You travel along the equator for a while, and then you take a 90-degree turn back to the North Pole. Well, at the bottom there, you can see that you've made two 90-degree turns. One to get onto the equator and one to leave the equator. So if the two angles at the bottom add up to 180 degrees, and the angle at the top isn't zero, well then the angles in this triangle must add up to more than 180 degrees. It's the curvature of the ball widens the angles, so they add up to more than 180. It's also possible for them to add up to under 180. You have to draw your triangle on a kind of saddle shape or a Pringle, the potato-based snack. If you draw a triangle there, that curvature pinches the angles, and so they add up to under 180 degrees. The correct answer to that question is it depends how you draw your triangle. Now, how this helps in space is that we can use the Earth as one corner of the triangle and then use two distant galaxies as the other corners. Measure the angles, see what they add up to. Turns out they add up to 180 degrees. So it seems like our universe doesn't have any curvature compared to the other two shapes. That might not be true, though, because if you were to draw a triangle in your back garden, the angles are going to add up to 180 degrees, even though your garden is on the curved surface of a sphere, curved surface of the Earth. Because in your small area of the Earth, the curvature is so minimal, you get 180. So it could be that the whole universe is curved like this, but that the piece of it we're able to measure is small enough that we don't notice the curvature on that scale. So the analogy here would be an ant on a balloon. You've got a balloon which has a curved surface, the ant's on the surface, you blow the balloon up to such a degree that, as far as the ant's concerned, its little piece of rubber is flat. The whole balloon is curved, but its little piece of it is now so big that it can't notice that curvature. So this could be the case for the universe. We could be like the ant and measure 180 degrees, even though we are living on the curved surface of a sphere. Except the Big Bang Theory tells us how much expansion there has been to get from the beginning to what we see today. And there simply hasn't been enough. There's not been enough expansion in that time to blow the balloon of the universe up enough to make our little piece of it look flat. So it's unlikely that we live on the curved surface of a sphere. It seems most likely that we live in a universe that is the bottom option. No curvature at all. Which opens the door to the possibility of the universe itself being infinitely big. Because if it was the sphere, if you walked out of your front door and you kept walking, and you ignored the fact that there are buildings and trees and even oceans in the way, and you kept walking, you'd come back to your house. You'd walk all the way around the Earth and come back to where you started. Your journey wouldn't be infinitely long. You return to the same point. But the sheet at the bottom, you can imagine stretching that sheet out. And just as the list of numbers never ends, you can keep adding more numbers. Well, then you can keep adding more sheet. So the universe could be infinitely big and have no edge or boundary. And that opens the door to something really weird and strange. Because the universe may be infinitely big, but there are only a finite number of ways of arranging things within it. So the analogy here would be, I give you 6 dice, and you roll those 6 dice. The chances of you rolling 1, 2, 3, 4, 5, 6 on those dice is slim. It's about 1%, 1 in 100. But if you roll those dice 1,000,000 times, you're going to get that pattern more than once. In fact, quite a lot. Because the more you roll, the more you get unlikely things. Having an infinitely big universe is like rolling the dice an infinite number of times. So you're going to get repeat patterns. Just like you'll get 1, 2, 3, 4, 5, 6 more than once when you roll the dice, you will get the same arrangement of atoms again. The same arrangement of atoms as they are exactly here right now. From the atoms in me, to the atoms in my voice box, to the atoms vibrating the air between me and the microphone, to the electrons in the wire that carry the sound to you, to the atoms in your ears that are hearing it, and the atoms in your brain that are decoding it. In other words, if the universe is infinitely big, it is guaranteed that there are copies of you and copies of me having this exact same conversation. In fact, there are an infinite number of copies of you and me having this conversation. And we call this a level 1 multiverse. But eventually you go so far into the universe, you get a repeat pattern, as you do here. There is a way, though, to solve this, a lot of the problems I've been talking about. So the problems like, how can something come from nothing? Where did the Big Bang happen? And what happened before the Big Bang? It's a modification to the Big Bang theory. It's a change. All you do is you add in a super rapid period of expansion at the beginning, which we call inflation. So we've been dealing with inflation of a different kind lately in the real world of prices ballooning. Cosmic inflation would be that at the beginning of the universe, it ballooned really quickly and then continued to grow but slower. The theory says that in the first trillionth of a trillionth of a trillionth of a second, the universe went from the size of an atom to the size of a grapefruit. doesn't seem like much. But that's because we don't really have a good idea of how big atoms are in our heads. We're talking about getting 10 with 78 zeros after it times bigger. Let's put that into context. Imagine taking a red blood cell from your body, the ones that carry the oxygen around. Take one of those tiny red blood cells and make that the same number of times bigger, 10 with 78 zeros after it. If you were to do that, that red blood cell would be now bigger than the entire observable universe. We are talking about a huge jump in size in a very short amount of time. And that helps us with this flatness problem. Because if you remember, we said, well, there simply hasn't been enough expansion since the Big Bang to smear out our local universe, so we can't live on the curved surface of a sphere. The whole thing has to be flat. But what inflation does is add in this extra period of expansion, some expansion that we hadn't factored in before. And that would allow this to, what you see here, to take place. It could be then that we do live on the curved surface of a sphere. And that would do away with the infinitely big universe that I mentioned before. The sheet wouldn't go on forever. It would wrap around and come back on itself. So we would get rid of all the other U's and all the other parts of the universe and copies of you. Kind of. Because when we work out what might have happened to make the universe do this, to go through this period of inflation, it seems a very hard thing to get it to happen one time only. It seems more likely that it would have happened a lot. It's a bit of a juggernaut that's hard to stop. So you would have this situation here of constantly fracturing universes. So at the bottom, the blue one, that is one universe. But within that universe, inflation happens more than once. And so you end up with 3 splinter universes. And within that one, inflation happens again. And so you end up with another universe out of that one. And then another universe out of that one. So you end up with these bubble universes, or what is called a level 2 multiverse. And then you get back to the same thing we had before. Not lots of copies of you within the same universe, but lots of copies of you across these different universes. Because if there are infinitely many bubbles, you're going to have the same pattern repeat across those bubbles. So there would be a bubble universe out there with a copy of you having this conversation. And even slight variations. So there'd be a bubble universe where everything is the same, but I have purple skin. There could be another bubble universe where you have the head of a duck, but everything else is the same. And in fact, that's guaranteed if there are infinitely many. All possibilities would play out across this level 2 multiverse. Now, the last thing I want to talk to you about before we have a chat is to show you how counterintuitive infinity can be. It crops up time and again in astronomy, but it's a really slippery customer. The person who came up with this analogy that I'm going to show you now is the person you can see, David Hilbert, a German mathematician, about the same time as Hubble worked out the expansion of the universe. It's called Hilbert's Hotel. Now, crucially, it might be worth getting rid of me for this one, so that there you go, thank you. Right, Hilbert's Hotel is a hotel with infinitely many rooms. So just like the counting numbers, the number of rooms never ends. It goes on and on and on without end. This hotel is fully booked with the exception of one room. It has one room empty in the whole hotel, room number 9. So a guest shows up, wants to stay for the night, and the receptionist shows them to room number 9. This hotel is now fully booked. Every room is full. Somebody else turns up asking for accommodation. Can this new person be accommodated in this fully booked, infinitely big hotel? The answer is yes. What you have to do is move everyone along one room. So person in room 1 goes to room 2, person in room 2 goes to room 3, person in room 3 goes to room 4, and so on. Because it's infinitely long, they can keep shunting down, and you put this person into room 1, a new person. If 100 people show up, you shunt everyone 100 rooms along, so 1 to 101, and so on, and you put those 100 people into the first 100 rooms. So you can accommodate any number of guests that way you like. I want you to imagine then that an infinitely long bus turns up. And on this infinitely long bus are an infinite number of people all wanting to seek accommodation in this fully booked hotel. Can they be accommodated? The answer is still yes. All you have to do this time is double the room number of the existing guests. So everyone in room 1 goes to room 2 to 4, 3 to 6, 4 to 8, and so on. Whenever you double a number, the answer you get is always even. So if you double an even number, you still get an even number. But if you double an odd number, you also get an even number. So by doing this, you occupy all of the even numbered rooms and you leave all of the odd rooms empty. Because there are an infinite number of odd numbers, you can fit this infinitely long bus of infinite people into all of the odd numbered rooms. Now I want you to imagine that an infinite number of infinitely long buses turns up, each with an infinite number of people on board, and all of these people want to check in to the fully booked Infinity Hotel. Can they be accommodated? Still can. It's a bit more convoluted, but you can do it. You use one way to do it. There are other ways, but one way is to use prime numbers. Prime numbers are those special numbers that can only be divided by 1 and themselves. So you assign the existing hotel guests the first prime number, which is 2. And then for each of the subsequent coaches, you give them the next prime number. So the first coach gets the second prime number, which is 3. So the first coach gets the second prime number, which is 3. The second coach gets the third prime number, which is 5, and so on. You then take, for the existing guests, their current room number, and you multiply their prime number, which is 2, by itself, the number of times equal to their room number. So for the person in room 1, the first prime number 2 multiplied by itself once is 2. For the person in the second room, you take the first prime number, which is 2, multiplied by itself twice, 4, and so on. So you maybe move me out of the way slightly again, then you'll see in the bottom corner, person in room 3 goes to room 8, person in room 4 goes to room 16, and so on. For the coaches, exactly the same thing. Person on the first coach uses the second prime number, which is 3, and instead of their room number, you use their seat number on the bus. And you do the same thing. It's possible then to give everybody, both the existing guests and everyone on the buses, a unique room number. And so everyone can be accommodated because there are an infinite number of prime numbers, 2. That is not the strangest thing about this setup though. Remember, before all these buses turned up, the hotel was full, completely full, and you've accommodated an infinite number of buses. But there are some numbers it is not possible to make this way using these prime numbers. You may have noticed that the first room number you get is 2. So what happened to room 1? You can't make 1 that way using this prime number technique. You can't make 6, you can't make 10, you can't make 12, 14, 15, and then infinitely more others as well. In other words, these rooms 1, 6, 10, 12, 14, and 15 are empty. So this hotel that was previously fully booked has now accommodated an infinite number of infinitely long buses with an infinite number of people on each and is no longer fully booked. It has empty rooms. And that is the ridiculous, crazy, counterintuitive thing about infinity. That when you start playing around with it and logicking out some of these things, you get to things like that at first make no sense, but then at the same time are fantastically wonderful. And so I've always loved infinity for 2 reasons. One, that marvelous ridiculousness of those kind of logical conclusions. But also from an astronomy point of view, it's like this. It is a glowing neon sign. If it pops up in astronomy from the bottom of a black hole to the beginning of the universe, it's telling you that there's something missing, that there's something you're not understanding, a missing piece of the puzzle. So it can be both ridiculous and useful at the same time.
Wow.
Thank you. Right. I appreciate that's deep for lunchtime.
Absolutely. Well, it had me thinking. And please, if you're watching this, can you please put some questions in the chat?
I appreciate that. Yeah, that is deep. But that's what I've been talking to the older ones about today.
Brilliant. So your love of maths, obviously, have you always loved maths and the universe?
Yeah, I have. So there were the two things I loved the most were space and maths. There's something reassuring about maths. Like other subjects, the answers can be a bit wishy-washy. It's subject to opinion, or there's nuance to it. You could argue, I don't know, was a historical figure a bad person or not? There's two sides to the story. You can't argue with the 2 and 2 is 4, like it's 4. So I really like the certainty of it, that there's a definite answer, and I really liked the kind of struggle of finding that answer. So there's something. I always say maths is simultaneously the most frustrating and rewarding subject in equal measure. Yeah. Because it can drive you mad, but at the same time, when you get the answer, there's some
Brilliant.
elation there.
And did you study maths at university?
I did astrophysics at university, which is incredibly heavily maths.
Yeah.
So all of it's maths, and so it's working out things like the pressure in the core of a star, which is 2 pages of maths. So yeah, there wasn't a maths degree, but it was, incredibly heavily maths-based. Yeah.
Tell us about your book.
Yes, so the book today, this talk is based on my latest book, which is Numbers 10 Things You Should Know. So it's 10 different things you might not have realised about maths before. The 10th thing is infinity, which is when I talk about the hotel that I've shown you here. But there's other things like, one of them is also about triangles not having 180 degrees, but other whimsical things like you've been cutting cake wrong. So the way we all cut cake, and this is the way I cut cake too, you have a piece of cake, a whole cake. You probably don't eat it all in one sitting, maybe you do. But what you probably do is cut out a triangle slice, give yourself a slice, put it in the tin, maybe put it in the fridge. But then those edges, they are exposed to the air, and if you're not careful, they're going to dry out. And the next day you come back to have your next slice of cake, you're going to have a kind of dry edge to your cake. So there was a mathematician in the early 1900s who wrote a serious scientific paper about the mathematically correct way to cut cake. So what you should actually do is take your cake and cut a slice down the middle, like a rectangular slice down the middle. You can eat that, squidge the cake together into a new circle. There's no exposed dry edge. Put a rubber band around it, put it back in the fridge. Next day, take it out, turn it 90 degrees, cut another rectangular slice from the middle, squidge it together again. And so then you have moist cake for 3 days in a row. So that's the other thing about maths, is that I guess sometimes it's often seen as quite serious. Yeah. But this was a proper serious mathematician doing proper mathematical research who thought one Christmas, when he was cutting Christmas cake, is there a better way to do this? And he wrote a paper on cutting cake mathematically. It's actually
quite fascinating. I don't think I'll ever cut a cake the same way again now. I'm going to
try I still don't cut it. It's a bit of a faff. I still cut it the old-fashioned way. But if you're being geeky about it, you should probably cut rectangular slices, not triangle slices. And
what you were talking about the probability that there is us somewhere else because of the infinite number of combinations and things. So that could happen absolutely anywhere, couldn't it?
Well, everything is copied. So there would be in both situations, either the level 1 where it's one universe that's infinitely big, or the level 2 one where there's infinite copies of the same universe. And everything is copied. But not just everything is copied, every variation is also there as well.
So if we were having this conversation somewhere else in the universe, it would be identical to what we're having now?
Yes. Well, the thing is, everything would play out. So there'd be an infinite number of copies of us having this conversation, but also an infinite number of copies of us having a very slightly different conversation. Right. So every different possible, whatever is possible is, if a universe is guaranteed, there is no probability, because every possible thing plays out. So it would be like, with the dice analogy, it would be like, okay, we rolled the 1, 2, 3, 4, 5, 6. That's exactly the same conversation we're having now. But there's also 1, 2, 3, 4, 5, 5, which is a very similar conversation. Yeah. But maybe we're talking about a different aspect of it. Yeah. Or you have 3 heads, or I have 2 legs, 3 legs, or whatever.
Do you ever stop thinking about this?
This is the danger of it. I'm okay now. I would say maybe 3 or 4 years ago, 5 years ago. I think before I had kids and had a bit more time. I did go through a bit of an existential funk for a while because there's other things as well. So those of you that bought a copy of the Time book for the kids, thank you. Some of you also ordered a copy of the Time book that's in the same series, and in that book, I also look at things like free will and whether we have choices in life or whether our futures are all predetermined for us. And our best theories of time tell us that the future is also predetermined, and that every choice we ever make was the choice we were always going to make. Who we marry, where we live, the kids we're going to have, that future is out there waiting for us and is unchangeable. And I mean, these things are quite...
It's very deep, isn't it?
It is very deep. I kind of start, I think about it when I do these talks, but in your own spare time, it would drive you mad if you did.
Yeah, I suppose, because I think we probably all feel like that. So we sometimes believe, everything happens for a reason, and it was meant to be this way, It was
funny because I really railed against that as someone who likes science and physics and stuff. The idea of a kind of fate or destiny when I was younger, I thought that was nonsense until I sort of learned more about the physics of time, and actually that's built in to our best theories of physics of time. So I thought it was kind of incompatible with science, that it was kind of wishy-washy, but it's actually baked into our best models. So what you're going to do tomorrow, what you're going to have for breakfast tomorrow, what you're going to have for dinner tonight, whether you're going to get stuck in a traffic jam tomorrow is all...
Wow.
It's all laid out waiting.
Yeah. So we could probably predict the future if ever we could crack this then, maybe?
Well, that's the thing. It's there, but predicting it is the trickier part of it. So the analogy I would use for the future thing is that time is a bit like a book. So the beginning and the middle and the end of the book are already written. So if you're reading about a character on page 50 of a book and they're caught in a love triangle, then it's going to be resolved on page 100 because that's what's in the book. They don't know it yet, and they might not be able to predict what's going to happen. But whatever they do next isn't going to change the fact that on page 100 it goes a certain way. So, but predicting what's going to happen, if you're reading page 50 of a book, you might be able to guess what's going to happen on page 51 because it's immediately the next in the story. But if I was telling you on page 50 to predict what's happening on page 150, would you be so confident?
No.
No, because it's further into the future, isn't it? So it's a bit like the weather. Our predictive powers for the weather, they're pretty good at telling what's going to happen tomorrow. But weather forecast for 5 or 6 days' time, we're always a bit flaky.
Absolutely. And, I'm a bit of an amateur mathematician. What about dimensions? We hear about coexisting and different dimensions and things we can and can't see. Can you explain that a little bit to me? I'm just fascinated by it.
Yeah, do I have... Let's have a look, whether I have it on here or not. I might have taken it out. So one of the issues we've got with the singularity, I was saying at the bottom we get this undefined error, and I said a singularity probably isn't what's down there. Well, one way forward might be to try and combine the Einstein's equations with quantum physics. And quantum physics deals with atoms and small stuff. If we could, because the singularity is very small, so if we could merge these two theories together, we might have a more complete theory that could describe what is really down there. But the trouble is, when you try and combine the equations of relativity and the equations in quantum physics, they don't fit together. They just generate nonsense, unless you invent extra dimensions. So if you assume that the universe has 11 dimensions, as far as we're concerned in our everyday lives, it has 4. The 3 dimensions of a room, plus a dimension of time. So I'm here now. The room's going to be here tomorrow, but I doubt I will be. So everything has 4 dimensions, a time dimension too. If there are 7 other ones of space, the maths works, and we can combine these theories. But then, if that's true, where are they? Where are these 7 dimensions? Well, the physicists would say, well, they're curled up really small, so we don't see them. It's convenient, isn't it? That you can't put these things together, and so you invent these dimensions, but then you go, oh, hang on a minute. They've got to be there to make the maths work, but then we can't see them, so you've got to squirrel them away so you can't see them. This is the kind of area of string theory. So the nice thing about mathematics is that you can work in additional dimensions to the ones that we experience. But the analogy I use is just because a comic book writer can write about Superman or Batman and superpowers doesn't mean people can fly. So you can write down equations in 11 dimensions, but there's no guaranteeing that it's real. So in summary, sometimes we invent extra dimensions to solve problems, but there's no evidence they exist.
I'm not sure that answers my question, but that's fantastic. And what about your star? You've got a star, haven't you?
Or an asteroid. Yes, not a star, but an asteroid. So one of the sort of things they can give out in the astronomical community is to rename an asteroid after somebody. So most of the time there's two ways. It's either a really famous person, so there's an Elvis Presley and a Freddie Mercury and a Rosalind Franklin and all sorts of genuinely famous people, or it's people that work in astronomy and have done important things in astronomy. And so for me, it was a kind of, they gave it to me as a kind of thank you for writing books, going into schools, trying to get kids interested in space. So they renamed this asteroid after me several years ago.
Yeah, and it's great because you're actually bringing maths alive to us today.
Yeah, that's the point. I mean, even with the smaller ones today, I was talking to year 5 and 6 first, and that was not about infinity, but about maths in the animal kingdom and about how different animals, from bees to ants to butterflies, have worked out the most mathematically efficient way to do stuff.
Yeah.
And that's the thing with maths. Sometimes it's seen as, well, what's the point, or why? What does it apply to? But it's all around us all the time. Like bees are building hexagonal beehives and all sorts.
Mm. And I actually was working with a group of year 8 girls last week when we were talking about Fibonacci.
That was in there too. Yeah, that was in the talk this morning.
Yeah.
For the years 5 and 6.
Absolutely fascinating, isn't it? Yeah.
So particularly, just to explain with that one, there's a particular sequence of numbers and things like sunflowers. The pods on the head of the seed of the sunflowers have a certain number of spirals that are all Fibonacci numbers, and it's just because it's a really efficient way of packing the seed pods into you get the biggest bang for your buck, right? You get the most amount of seed pods in a small space.
Absolutely. I mean, it's really fascinating. If we've got any questions, we haven't got any questions come through.
No, I appreciate that it is deeper than perhaps normal.
But it's wonderful, and you've explained it so well as well. I think when we're talking about the dimensions, it's just something being a bit of a deep thinker, you think about these things and you hear about things, and you put it so well about where and why and how things are there.
Yeah, so I think that's just what I really like about this kind of stuff is that you take a question, and normally it's a kind of simple question, and then you start pulling at it, and then all of a sudden it unravels into this mess of existential crisis.
So what are you working on now? Are you working for something in particular?
So I've just finished a new kids book about aliens and the search for, but not in a kind of sci-fi sense, in a science sense of how we try and find alien planets and work out whether we're alone in the universe, coming out about this time next year, I think. And then I've just also finished an astrophysics for beginners course. So I used to teach these courses online in a kind of Zoom webinar kind of a way, a bit like this, but I've now made them pre-recorded so that you can kind of access them in your own time. And, so this sort of stuff about black holes and the Big Bang is all in there.
And what advice would you give to our young mathematicians? Enjoy
it. I think that's the thing. It can be frustrating. I think I've never encountered a subject that is more frustrating than maths. But that's part of the fun of it, I think. Yeah. The same thing about doing a jigsaw puzzle or whatever it is. There's a bit of, you've got to work at it, but it's like a language in the way that you're not just going to speak French straight off the bat. You've got to learn how the structure of the sentences works and the different words for things. It's the same for math. It's a language, and the more that you practice it, the more fluent you become in it.
And it's quite beautiful as well, isn't it?
It's so beautiful, and I think that is the thing about it. Some of the patterns and things, it is.
It's mysterious.
There's something about it. I think even though that my main thing is space, I've always had a real soft spot for maths because the two go hand in hand anyway. But all of this patterns and puzzles, and it's fun.
Brilliant. Well, Colin, thank you so much. I hope you have a great rest of the day. And
no problem. Thank you for having me.
It's been lovely to spend this time with you. So thank you very much.
No problem. Thank you.
Thank you.